India confirmed that it had launched airstrikes on 9 locations in Pakistan. The military confirmed 3 locations have been attacked, including a mosque. It then responded, firing artillery across the border into Kashmir. It comes after a deadly military attack on tourists in the same region last month.
Hello.
Adrian vào lại. Phải là sai. Let's start first. When more people come, we'll update on you on the assignments. Okay. So last week what we play around is topological space. Okay, so what's a topological space is? It's just a set plus a collection of subset. Or I just call it set of subset of X. Okay, or in other words, this tau here is a subset of the tau set of X. Okay. Which we call the element inside here are the open set. Okay. So open here means what? What do you think? The open here? Open means what? Good. So first, you have to close under finite intersection, and then close under arbitrary union. Good. Any more? Okay, so the empty set and the full set must be one of the open set. Okay, that's all. Okay, this is open. So notice here, I didn't use any open ball yet. I think. Okay, we just extract the the properties of open ball. Open ball will satisfy all these properties. Okay. Okay, so this is the idea of open set. So you see, so you can see that last time I demonstrated to you that for one set, right, I can pick different collection of set to be open. Okay, then we can talk about what's their relation. Okay, we can talk about what's the relation between two different topology on the same space. Okay. Okay, consider two topology here. So all of them are collection of subset of X, right? So maybe they have non-trivial intersection here. Maybe. Okay, maybe they will have non-trivial non-trivial intersection here. Okay, for example, let's say what if tau contain T? Okay. So if every element in tau is in T prime, we will say that we say that tau prime is finer than tau. Okay. Or we will say that tau is closer than tau prime. Okay. If in the case that you have a strict inclusion here, we will say that tau prime is strictly finer than tau, or tau is strictly closer than tau. Okay. Actually, in some of the literature, you'll find that there's another way of saying it. So if tau prime contains tau, right, I will say that tau prime is actually larger than tau, or tau is smaller than tau prime. Okay, think about it. Okay, think about it. Do you think these two definition kind of like a contradicting idea? What is finer? Fine sort. 知道什么叫 fine sort? Fine sort. 知道什么叫 fine sort 吗？ Anyone know what is a five sword mean? 什么意思？表 U 的啥？好，表 U。Okay, if tau prime contain T, we say tau prime is final. And then obviously the others should be closer. But here I say tau prime is actually larger. 到底它 U 小还是 U 大？到底是大还是小？啊？什么？大不小。Okay, so let's look at some examples. Let us think about how we interpret this final and larger. How to make sense of both of these adjective here. Okay, so let's look at some examples here. So just look at the topology on a 3-point set that we discussed last time. So last time we agreed that there are 9 types of them, right? So let's write down 9 of them. So we got tau 1, tau 2, tau 3, tau 4, tau 5, tau 6, tau 7, tau 8, and tau 9. Okay, so all of them should start from a set of 3 elements here. So the whole set and the empty set should appear together. That should at least has the whole set as an open set. Okay, so let's say T2 is this singleton set. T3 is this set containing 2 points. Here, got 2 set, 2-point subset, 1-point subset. And the other one, we split these 2 up. And then here, we got a NOS-like structure, topology. This one, we have a open set inside the intersection. And then this one, we have one more extra. And then the last one is the discrete topology, where we include all the possible subset. Okay, so can you reckon which tau live in which tau? Which tau contain which tau? I'll give you an example. For example, T2 will contain T1. Correct? Okay, can you give other example? T6 contain who? T7. T6 contain T7, correct? T6 like this, right? For these 4 things. Nani? Oh, sorry. Yes, thank you. So T6 contain T9 or not? The other way around, right? Because T9 got literally every subset. T9 doesn't contain just T6, right? It contains actually every T. Okay, actually T1, T2, up to T6. Others, eh? Any other non-trivial containment here? T4 contain T3, good. Who? T8 contain T7, good. T8 contain T7. T6 also contain T3. T6 contain T4 and T3. Okay, so actually you can form a chain here. Okay. And then T7 also contain T3. Okay. 6, 4, 3. T7 also contain T2. T6 got T2 or not? T6, yeah, T6 contain T2. Can we put 3 and 2 together? No, cannot. 4, eh? 4, no. Okay, so T6 contain T2. Okay, good. Okay, so what can you see here? Which one coarser, which one finer, which one bigger, which one larger? So larger and smaller here. Okay, just pick one example and see. Let's pick 6, 4, 3, and 6, 4, 3. 6, let me draw. So let's look at 6, 4, and 3 here. Okay, 6, 4, and 3. So we say that T6 is finer than T3 and T4. Okay, because it contains these two. Why is it finer? Because you have more subset here. More subset. You can see even more stuff inside T6 than T3 and T4. The coarsest one should be T1, right? Because T1 contains in everyone. So in T1 here, you can only see everything or nothing. So you cannot see these other subset. So it's coarser. Correct or not? Okay. So why is it finer? Because there are more subset here. Okay. Why is it larger? Contain more subset. Okay. So this is the idea. Okay. The whole idea is you have more subset. More subset to be open. Okay. So you see this one is coarser. The trivial topology is coarser. It is the smallest one. Yeah, it is the smallest one because you only have the whole set and empty set to be open. Okay, it's the smallest, it's the closest. You cannot see more open set. Okay, does it make sense? Okay, so when you have two topology, you could compare them. If there's inclusion like that. Okay, then for examples, then T5 and T6 cannot compare. Okay, something that T5 have, T6 doesn't have, which is this circle here. Something that T6 has, T5 doesn't have, is also this circle that contains it. Okay, they cannot compare. You cannot say which one final, which one closer. Okay, they see different thing. Okay, not. Yeah. Unless you can see everything what the other topology can see. Then you can compare. Okay, that makes sense? Okay, so this is about final closer here. Okay, next we will go to basis. Basis for Hey, Zhao Shen not here yet. Sleeping. Okay. So basis for topology, this basis is rather different from the vector space basis. We are not trying to write something as a linear combination of something, okay? But they have a basis property, okay, which they can be found in every open set. In some textbook, right, you will see they call them base. Okay, so base and basis is the same thing in the general topology. Okay, so we will use the word basis. We try to link this basis to vector space if possible in future. Okay. So again, let's start with a set. What's the basis here? Again, basis for topology is just a collection of subset. Again, subset of subset of X. Okay, and then these element we call them a basis element. Okay, basis element. So open set could satisfy some axiom, right? So here also satisfies some axiom here. Two things you need to satisfy. First thing is for every point in your X, okay, you need to make sure that there's one element from your collection, let's call it script B, such that X will contain inside this B. So you need to be able to protect every element in your topology. Okay. If you are the basis, okay, you want to form a basis, you need to be able to contain every point. Okay. Not just one B that work for all X. It's every X you could find some B. Okay, so meaning what? Meaning this B here could depend on X1. Okay, could change based on X. Second is a very special property here about topology here. You need to take note here. If your X is contained in two basis element, okay, contain two basis element, that means you can further refine it, find another element in your script B such that X is living in this B tree. And moreover, okay, moreover, this B tree is living entirely inside B1 intersect B2. Okay, so I can summarize this into a picture. So in this class, right, make sure you have a lot of picture inside your mind. So, okay, you have a set X, okay? Then we want to talk about maybe some point inside this X here. So our first point says what? You must be always, okay, able to build a basis, okay, basis element around your S, okay, that contain it. So let's call this the X here. And the other things, if this point here live inside two, okay, basis element, let's call it B1, B2 here, B1, B2 here. You must be able to find another smaller one that live entirely inside this intersection and also contain X. Make sense? Okay. So one is containment property, the other one is an intersection property. Okay, these two things are all right. So then we will try to build this topology using this basis element here. So if if there's a set of element that satisfy these two condition here, we're gonna build a topology out of it. Then we will define what is called the topology generated, okay, by this basis here. The topology how that's generated by E. Okay, so meaning what? When we talk about topology, right, I need to tell you how to declare something is open. Okay, so now we're gonna declare something is open based on the B we had. Yeah, based on the B we had, we want to declare something is open. What do you think? What do you think? How should we define open here? Based on B. No, we want to define U is open. So how to define U is open based on script B. So you see, the picture I draw hinting you what? Open ball. Seems like open ball inside Rn satisfy this property. Correct or not? Is it true or not? So the picture I draw here kind of hinting that the open ball inside Rn will satisfy these two properties. If you have two open interval, can you find a smaller open interval in the intersection or not? Is every point live in some open interval or not? So how do you declare something open there in Rn? Do you still remember how we define open? How? There's an open ball, right? So these are like the open ball here. So meaning what? We declare that U is open if for every point in this set here, there exists a basis element such that such that this B will contain X, and then this B is a subset of U. Okay. So we are using B to define what opens B. This is called the topology generated by basis element. We don't know B is open or yes, very good. So the next thing you need to do is a sanity check. So what do you need to check here? You need to check that this topology is indeed the topology, indeed a topology. Okay, so we need to prove that the open set we define here is actually following the tree axiom. Okay, maybe for the first time I will show it to you how to prove this. So like what Zhengye suggests just now, right? You need to check for open set and empty set and the whole set. So why empty set is empty here? Sorry, empty set is empty. Why the empty set is open here? So if you want to check empty set is open, right? You check for every point in this empty set, but there's no point in empty set. Okay, so it is open vacuously. Okay, so it's always true then. How about X? So if you want to show that X is open, right? Meaning you need to show what? For every X in X, there exists a B in script B such that B will contain B will contain X and then contain in U. What does this script B give you? There are two things that script B give you, right? One is containment, one is intersection property. So the containment, what does the containment do? Every point in X, there exists a Bx, okay, such that S is in Bx. Okay, so this is the first line that this basis element did for you. Okay, by part one, there exists a B in B depending on X, such that X is in B contained in X. Okay. So the first one, actually, it's the first property of basis element tells you that the whole set is open. It's open. Second, which one should we do first? Let's do intersection. We want to prove that finite intersection is open. Okay, but we're gonna do using induction. Okay, using induction on K. Okay, so meaning we just do intersection of two sets first. Okay, let's take two open set. In T, we want to show that the intersection also live inside T. What to do here? Again, you need to use this open definition to check whether it's open or not. Okay, whether you want to check that the intersection is open or not. Okay, so what do? You need to take any point from the intersection. Okay, any point from the intersection. What does this mean here by set theory? Hey, if X in the intersection means what? X is in. But you repeat my word. What does living in intersection means? X live in. What's the definition? X live in U1 and X live in U2. Okay. But by definition, U1, U2 are open. Sorry, not by definition, by assumption. U1, U2 are open. Okay. But definition of open here means what? Can recall again. Open in topology generated by basis element. Meaning what? For every X inside this open set, you can find a basis element. Okay. So there exists B1, B2 in B such that X will lay inside B1 and B1 contain in U1, and also X will contain B2 contain in U2. Okay, I see X live in B1, X live in B2 means what? 同时活在两个地方 means what? Then X will live inside the intersection of B1 and B2. But now it's special, right? You are living inside the intersection of basis element. This now basis element will satisfy what property here? There exists another. So by 2, there exists the third basis element here. Such that X will contain in B3, contain in B1 intersect B2. Okay. Okay. Now. Okay. Are we done yet? What do you want to show? We want to show that U1 intersect U2 is open. Meaning what? We want to show that there's a ball inside U1 intersect U2. So is it true that this set here is a subset of U1 intersect U2? Is it true or not? True. Why? Is it true? Why? Which one is in U1? You take X is in U1 intersect U2, and then B1 is U1, B2 is U2, and then and then this whole. But to show that this whole, right, you need to show that this intersection living in both of them, right? U1 and U2. Why? You only know that B1 is in U1, B2 is in U2 separately, right? So okay, so let me write here. So since okay, let me put here since B1 is in U1, B1 intersect B2 obviously is in U1. Is it? B1 intersect U1. B1 intersect U1 is in U1. Sure. Okay. How? So you say B2 intersect B1. intercept U1 equals to B2 intercept B1. And then think about it. Try write it down. U2. You want to intercept with U2. And then which bracket you want to take? Okay. B1 and U1. And then okay. U1 equals to stuck. Any other attempt? Okay, so B1 intercept B2 is a subset of B1, which is a subset of U1. Similarly, you can play the same game to B2. So B1 intercept B2 is a subset of B2. So it is all, but we know that B2 is also a subset of U2. Okay, so we can show that the intersection here is a subset of two U1 and U2. So can live in the intersection. Okay, no. Any question? Okay, so this is nothing trivial here. You need to write it down. Yeah, it's not directly you see B1 in U1 and then B2 in U2, then write it. So please take note. Okay, so then you can apply this inductively to finitely many intersections. Okay. So you extend. Okay, so U1 intersect U2 will live inside top. And we extend the result to U1 intercept up to UN to U1 intercept up to UN minus 1 union intercept UN. Okay. So try and write down the induction step here. So by induction hypothesis, right, UN minus 1, the intersection up to UN minus 1 should be open. Okay, and then you play the same argument to this two open set here. Okay, if you don't know what I've been talking about, please try and write down. Okay, third, how about arbitrary union here? So how about arbitrary union here? So if you take an X from this arbitrary union means what? Union, set theory again. You live inside a union means what? X will live inside one of the, let's say call it beta here. But we already know what do we know? By assumption, this U beta here is already open because this guy lives inside tau already. It's already open. Open means what? There exists a B in the basis such that X will contain in this B contain in U beta, but U beta automatically contained in the large union. Okay. Okay. No? So you have demonstrated that you can find a basis element that sit in between X and the union. Okay. Hey, the way that sit is a bit different now. You need to be careful of element of and subset is different now. Does it make sense? 不一样哦。Be careful. Actually, there are two sentences here, not one sentence. One is an element of a set, and then the other one is a subset inclusion. Okay. All right, let's give some example here. So just now, what are the example here? What are the basis element? So for example, all the circular region, or more precisely, the interior of circular region in the plane. So in this case here, we just talk about R2, for example. C2 also can. Okay, so what are these? These are the ones that we have drawn just now. The open bowl. Let's use the other color. Okay, these open bowl. Okay, so you can find some point, okay, that avoid the boundary of this intersection. Okay. What else? Actually, there are easier basis element here. For example, again, we use plane again, using R2 again. Hi, hello. Did you bring bak kut teh for us? Next time you can spend your cycle time to buy bak kut teh first. Make full use of your time. Okay. All the interior of rectangular region, okay, in the plane. Okay, meaning what? Any rectangle, I take it as a basis element. So what's the picture looks like? So let's say we take two rectangle here. Okay, and then there's a point inside here. So what can you see here? Maybe you will think that I need to take a smaller one to live inside this intersection, but actually, the intersection of these two rectangular region is already rectangle. No need to be a smaller one. Automatically a rectangle already. The same thing. Okay, but the intersection between two open the circular region or the open this here is not a this, so we need to find a smaller this. Okay, okay, unless you include this kind of thing inside your basis, then you don't need to create a smaller one. Okay. Okay, sometimes when they intersect, they are already a basis element. Let's all be careful 不用特地去做一个更小的东西出来不要死根了。OK， 这种就叫死根然后你就跟错东西其实它不是重点。OK， 重点是那个圆圆的 intersect 它不够圆我们要再做一个圆的。Okay. But for rectangle one, when they intersect, actually, it's also already another rectangle. Okay, no need to build a smaller one. What else? Another very trivial one for discrete topology. What is the basis? Do you know? Let's say I want to build a basis for my discrete topology. For discrete topology means what? Discrete topology means what? Hey, what is discrete topology? Or you take all the element inside your power set to be open. Okay, so can you imagine a basis element that can do that or not? That can help you generate the basis, the discrete topology. Can you pick a basis that can do that, such that all the power set is open? All the power set contains what? I mean, all the power set, how to say? Yeah, all the power set, what's the smallest element? Can I say smallest element inside of power set? What's the smallest one? Huh? Sorry? Empty, empty, nothing to do with empty, right? Empty, there's nothing there. Maybe a bit higher than empty, a bit larger than empty. 我怎么 trivial 是什么东西？啊，trivial 是什么？啊，smallest set inside your power set. Singleton, no? Okay. So if you take all your singleton, you can declare that every element in your power set is open. Correct or not? Let's try this. So in this case here, if you take any open set called what? Let's say called P inside of PX. What did you see here? Every X in P, okay, what do you have? X obviously contained in the set containing X. But at the same time, this have to be a subset of P. Why? Because this X you pick from P. Okay, this X you pick from P. So this X should contain it. So it's a subset. Okay, almost is a tautology here. Can we relate this to isolated point? Let me think. Not quite actually. Later we will see how we use topology to define isolated point. Yeah. Okay. Okay. So another exercise you could do is prove that these are all basis elements. Okay, they form basis. Okay, check the two property. Okay, a very good exercise to check. Okay, next we'll go to lemma. So first lemma you're gonna see is let X be a set and B be a basis for topology. Tau on X. Again, then another way to talk about tau, right, is just you are taking the arbitrary union of these basis elements. Okay, arbitrary basis of element. Okay, we're gonna show this. So this lemma will tell you that when we talk about topology generated by basis element, it's just an arbitrary union of basis element. That's all. Okay, although just now we defined that something is open if you can find a ball inside it. But in essence, it's just an arbitrary union of basis element inside this topology. Okay, one direction is obvious. Which direction? There are two directions here, right? Left to right, right to left. Which one is obvious? Right to left, good. 你讲的. Okay, why? Why is it obvious? Okay, just now we already show what arbitrary union of open set is open in this topology here. Okay, so because these basis elements are themselves open because they contain themselves. Okay, and just now we show that arbitrary union of this kind of open set should be open. Again, now we are left to show the other side. Okay, so to show the other side, what do? We want to show tau live inside. Yeah. So we want to show this the other direction here. Okay, left to right. So element in tau is what? What is the element in tau here? Tau is a set of open set. So you need to consider an arbitrary open set U in tau. Then you want to write it in some form like this. Okay, this U should look like some union. Okay. So we want to show that U equals to U alpha beta alpha. Okay. If we want to index this, we need to find an indexing set for some indexing set here. Okay. We want to write it as a union. Okay, what sort of union you want to write it to? Okay. So you see, from one equality, right, we go to show the other equality here. Okay. So here, this equality is a set equality again. Okay, but this happened in the space of X, the set X. Right. Okay, so how are we going to find this B alpha? What do you think? Which B alpha will work? Which B alpha will work here? U is open says what? What does U open says mean? U opens mean every point in U that exists a basis element that contain X and contain in U. Okay. So one thing you could try is all these Bx. Okay. One thing you could try is all this Bx here. Then what do you see here? For all X in U, they will have a Bx in P, such that X is in Bx and then contain in U. But you see, if you look at every point of U, all this Bx will live inside this U here. So can you imagine or not? Okay, if you draw a set U here, no matter what point you pick, okay, no matter what point you pick, you form a Bx around it. And then this Bx here should live inside U. So meaning what? If you take the union of them, follows that if you take union of them, it will contain in U. Does it make sense? But I claim that this inclusion is equal. So meaning the other inclusion works. Why? Actually, it's pretty obvious. Why? Why the other inclusion works? Why everything in U is in this Bx? Huh? Why? How we choose this Bx? From all the point in U, so every Bx here will contain one point in U. Okay, so by construction, U is contained in all the Bx, union of all Bx. Okay, so here there's some counterintuitive thing happening, If you look at this picture 如果你看这张图我选这么多点我一直照这个圆圈你会感觉到有洞，对不对？就感觉到有洞嘛，好像填不完诶。But the point is, you can keep finding the point and then fill it in, fill in. 有洞再填，再填，再填，再填，填到 this lemma tells you that actually is the same set you started with. This is the power of this basis element. Okay, open set. Yeah. What do you mean normal circumstances? Then in what context then? Ah, open ball, yeah, open ball satisfies this because open ball, the Euclidean. Okay, are we proving this now? And yeah, later we will see that actually Euclidean topology is a topology that generated by open ball. Yeah, come on, say again. Why is it powerful? Well, powerful meaning you can describe all the open set just using these basis elements. Okay. So for example, in this picture here, this open ball is also open here because you can find a rectangle here. But this theorem tells you that you can build your open ball using rectangle. Crazy or not? So how to build it? If you go through this proof, find point here, build a rectangle. Find point here, build a rectangle. Find point here, build a rectangle. Build. Use rectangle, fill out all the empty spaces that you see. Okay or not? Yeah. Okay. So 你看有角角的东西都给你变到没有角角去。So this is about topology. It doesn't matter the geometry, angle, nothing one. No angle, no geometry. Okay. The circle thing is the same as the rectangle thing. Okay, that's why it's called topology. As long as it's under continuous deformation. But we will see more later. Okay. Okay. So another thing I want to remind you is this union is not unique. Is not unique presentation. So for examples, if you look at the open set in 0, 1, right, you can write it obviously as a union of two open set lah. But there are a lot of way, right? So maybe you can split it at 0.5 and 0.45, or you can split it at 0.45 and 0.4, for example. Okay, this is not unique. Right? It's a not unique way to write as a union. So not that I purposely picked there's a non-trivial intersection there. Okay, if you like disjoin them, then you will miss some point. Okay, no. Because we're just taking unions, so that's fine. Okay. Any question? Any question or not? Okay, if no question, let's take a break until 11:04.啊，我雷自己。好，什么意思？嗯哼，怎么这个呢？如果他做出来没事情，嗯 不知道。OK，肯定要有那粒东西嘛，肯定要有那个点，至少肯定要有那里。啊，就这样吧。That's it。哎，刚才我们做那 discrete topology 的时候的 basis 就是只有 contain 一个点，这样就 contain 一个点，single 灯就好了。不需要，你可以，但是不需要。
对，就
single 灯就够了。
我刚好这个问题，
什么？
就是一个 basis 它可以包括额外的东西的。
可以，有时候你会造出其他的 topology，有时候你会造出其他的 topology。
比如说，有没有可能它造出同一个 topology 还是包括？
可以啊，可以啊，你就讲可以啊。比如说刚才那个 discrete 嘛，你再丢多一点东西下去，它也是 discrete。
哦，是。好，那我们能不能定义出一个什么，比如说最小的 basis 之类的？
可以，可以啊，
有专
可以啊。
门的人定义。
好像没有人去 study 这样东西吧，但是可以，smallest 合理啊，因为你可以数嘛。但是你看哦，这个是 infinite 哦，这样你就很难 compare 哦。通常都是 uncountable。I mean， 如果你不 finite，
没有，就类似于那个 complete，类似于 Hilbert space 的 complete normal basis，那个叫什么 complete also normal basis，可以定义一个最小的那个。
嗯，
什么？
哦，
这个什么样 basis 可以跟那个 linear algebra 是上的？
啊，
蛮可以哦，可以。
I think 要在蛮 restricted 的 circumstances 下面吧。
这不是来 consider topology of vector space 是不是？
不是，你的 topological space 可能要蛮 restricted 的吧。Otherwise，可能 basis 会太大。我不懂啊，我只是来那个 claim 吧。我觉得啊，Yeah，
在 topological space 里面，你讲什么 vector space
vector space 是一个 topological space，因为你有 norm，你有 norm 你就可以说明。
因为之前有些就不能对接啊。
对啊，不能对边。对，
它的 content 不是讲多少
对，你想说
在里面，
啊，是啊，是啊，content 本来就没有在讲多少的东西
因为来你放到越大就是
啊
同类型，
啊啊，Yeah，I mean 就 Yeah，它就引着 context，
写错了，
没有写错啊，什么写错？
它是
写什么呢？
more subset
啊，OK，它少了一个 containment。Yeah, I mean, I hope to draw some formal connection. I think there could be some, but I think it's after quite a little. 这个面积这个啊。Obviously, one you have to go. Yeah, I think you have to. I mean, in the context maybe, in the context of more.
白的，白的这些颜色的话，它是太看不清楚，它这里颜色有点用红色、深色、橙色。
Okay, before we start, I think most of you are here. So one thing is I booked time for exam already, so it's Friday for our venue. And then the other thing is we need to do revision. How about week 7? Friday or 就 compare 一点2到4，我可以早一点或迟一点。Yeah. Okay. So, yeah, revision 嘛。Okay. So before that, if you notice, actually we delay in the lecture. Why? I can explain you to you why. Because last time when I taught this class, right, the student delayed my assignment. Okay, so we didn't discuss assignment inside the class. Yeah. And then so because we spend time discussing assignment in class and also we delay a bit on lecture 2, so we kind of delay 2 lectures about 2 lectures. So now I think I'm gonna catch up. So meaning week 6, now week 6, right? Week 6, week 7, I should finish up up to continuous function. Okay. But your assignment is containing continuous function. Okay, but for sure, I think this week you could do up to Hausdorff stuff. Okay, but continuous function you can leave it to next week, or if you have to look advanced also can, because 1000 already started basis before I did. Okay, so you can look at my blog. Johnson comment that this assignment file is relatively easier, so you can try. Okay, so you can try first, right? Okay, I think we will make the deadline next week. I can give you a bit time until next Friday. Next Friday for assignment. Yeah, for assignment 5. Okay, not so rush. 什么 ？Next Friday. So 今晚你们还来吗？你们来啊 ？OK， 如果你们来的话我就来。OK， 你不来我就不来，你来我就来。然后我们今晚可以去吃宵夜，带我弟去吃宵夜，因为有家人在。哦，对，是。我带我弟来做功课，他下个礼拜是考试。Okay, but anyway, what else? Okay, yeah, revision. So come back to revision. So revision. So our test is week 8, right? So there are few choices, lah. You want to do revision on week 7 or before exam? Week 8. Week 7. So which day? What do you think? 对，什么时间你们觉得？晚上拜六礼拜？Big revision。拜六礼拜。It's not physical, can be non-online, but someone must attend. 懂什么意思吧？不一定全部人都要来，你可以有理由不online，但是一定要有人存在在课室里面。我不知道，你不要问我啊，这种乖乖的规则啊，乖乖规则一定不是我造的，这种是学校对乖的规则，不是我造的。OK， 所以你们觉得怎样？发的电 revision 发，这样招生每个星期要回家，所以他应该有话语权。要回家的没有回家。要 weekend，OK，then weekday 晚上也可以，还是就是拜三晚上啊？怎样 weekday 拜到晚上 weekday 拜到晚上，下个拜到晚上 revision 啊？下个拜到晚上咯，就是你们每次来做 revision 就那我们也可以顺便讨论 assignment， 如果有必要的话。Okay, during this revision, what we're gonna do is, okay, few things you need to prepare. Go do your tutorial question first, okay, and then we will discuss assignment problem. Okay, all of them. Even if cannot all of them, because we haven't. Okay, depends. See how I gonna discuss assignment 5. I will cut down the content for you. I will tell you what to focus for your papers. Okay, and then okay, do your tutorial question, and then we will discuss assignment up to assignment 4. Okay, and then tell you what's the tips in exam, and then if you want to discuss assignment 5 also can. Yeah, these few things do together during this revision course. Midterm 有没有提供 还不至于了。OK 了。对啊，没很难吧？我希望不难。好像不难。哦，对，我还有一个 test practice。Okay, please do it. We will discuss that also. The practice test question. Let's try and do it. I posted it already. OK， 哎，Ivan 又没有在哎，Ivan 在哪里？消失啊？啊？OK OK，诗音呢？诗音从麻坡回来了吗？诗音从麻坡回来了吗？OK，讲嘛
好自律。
6点前去操场跑步。
？OK，
你饿了不理
6点才睡，
早睡就是好。
早。OK OK，let's continue，let's continue。Okay, next lemma. We'll prove a rather obvious lemma here, but it's non-trivial to write down the proof. So let's find a set. Okay, this special set is special. Why is it special here? How we're gonna take this set is we'll take all the open C in X such that for every open U in X and for every X in U, what we're gonna do is we put this C in between X and U. 哪一个 script 哈，这个 script C script C。Okay, so we take open C in X such that for all the other open set in X, for all the other open set in X, you can put this C in between the point of U and U. Okay. So this C here will contain contain a point in U, and then it contains in U. It's a subset of it. Hey, when we say contain and contain in, you need to be careful. Contain 包含 contain in 怎么讲呢？在里面，就在里面了。OK， 好。Yeah, be careful contain in 还是 contain？OK， 对吗 ？Contain inside, contain in, contain in where 或者 contain 什么 ？OK，be careful. And then usually I think for English most of the time we use contain for subset and element. So you need to be careful. Okay, whether we are talking about element or we are talking about subset. Okay, then the claim is this kind of set, right, form a basis. Form a basis of topology, and then this topology is the topology that you started with. Okay, there are two things to show here. This set of things form a topology. Okay, you need to prove it. Second thing is the topology that you form is actually the original one. 就是那个原本的了。Okay, so this theorem tells you what? If you start with a topology, how do you find basis? Go and find a set C that satisfies this condition here. Then this is the basis for your topology. Okay, so the previous lemma is we start with basis element, form a topology. Here is start with a topology, find the basis. Okay, so this script C here is the basis that satisfies this condition would be your basis. So like what I remind you just now, in this basis business, right, it's not unique. Okay, it's not unique. Okay, two different bases can create a topology, same topology. Okay, it's not unique. Okay, so for example, just now the discrete topology, we just take basis element as the singleton set, right? You can imagine if you throw in more open set into it, you still get the discrete topology one. Okay, because the point is the singleton set already inside your basis. Okay. All right, so You want to prove, what do you want to prove here? You want to prove that I found the basis. So bases have two property, right? What's the first property? For every x in X, then there should exist a C in the script C such that X should contain C, X should contain in C, and C is in X. Okay, is this true or not? Why? How to trigger the condition of this step here? You need to start with an open U. So your X should be open. Okay, since X is open. Okay, you have this condition. Does it make sense? 明白吗? You want to trigger this condition here. You need to start with what? Open U. But your X is open. Okay. Okay, second condition. Second condition says what? The intersection condition. Okay, suppose that X live inside C1 intersect C2. Okay, you want to find the C3 that contain X and live inside this intersection. Okay, so what do you do here? In topology, it's like algebra one. You cannot play too much game here. There's only very few assumptions you start with. What you know? You only know that C1, C2 come from C. So they are open. Okay, so since C1 and C2 are open. Okay, in particular, we have shown that final intersection is open, right? Okay, then you already have an open set. You can trigger your condition on your set. So by the construction of script C, what can you do? There exists a C3 in script C such that X is living inside C3 and then C3 live inside the intersection. Okay, so you see, we cleverly constructed this basis set here. Okay, we cleverly constructed. Okay, one last thing is we want to show that T equals T prime, where T prime is the topology generated by C. Okay, because we know that if we have a basis, right, we will generate a topology. But it's not clear that why these two are the same. Okay, but the lemma claim that these two is the same. Okay, it's the same. So we're gonna prove this. So show that these two set is the same, right? Two subset inclusion. Okay, which one we do first? Let's do T in T prime first. Okay, so if you want to show T in T prime means what? Every element in T must be in T prime. But element in topology is what? Open. Okay, so let's take a arbitrary open set here. Okay, we want to show that U is open in T prime. Or U is in T prime. That is U is open in T prime. Okay, so well, we got not much choice here, so let's do it. So suppose X is in U. Okay, since U is open in tau. Okay, by construction of script C, what do we have? We can find a CX in script C such that CX will contain contain X and contain in U. Okay. But what? But actually, this is what topology generated by the basis element CX means, right? Okay, you can find something in the basis element. This is what this topology generated by basis element. 还记得吗？刚才 how to declare open in the topology generated by basis. As long as for any open set, you contain a basis element that contains. Okay, this is what this is by definition of topology generated by basis element. Okay, how about the other direction 呢 ？OK， 凭什么说你做的东西就是活在我原本的套里面 ？Why? So suppose W live inside tau prime. Okay. Why do we start with the same tau? Okay. So by previous lemma, right? What do we see? Actually, we see that W can be written as a union of C alpha. Okay, 对吗? Just now. Just now we said that topology can be written as a union of the basis element, right? Okay. But not that. How do we call this C alpha? 我们从哪里选的 C alpha 其实 Actually, they are open inside the original topology. 那其实是从原本的 topology 那里来。So and hence, the arbitrary union of these C alpha should be living inside tau. OK， 所以其实为什么你讲我不一样？我明明就是用你里面的东西做出来的。所以说 they are the same. Okay. Understand? Okay. So the way they constructed it also point that they are the same topology. Yes. Burger is the same as salad. Why 啊？东西一样咩？哪一个一样 ？Salad 有肉有菜，有菜有肉。Salad 有菜有肉，salad 有肉哦。有面包吧 ？ham 哈，你说 ham 哈，有时候有 ham。英英啊，英英是什么 ？proton 不懂啊，面包对面包一样，有肉咩？我是说，有时候有 ham 啊，但是比较少是没，比较多是没有啊。熏鸭呀 roasted duck。Yeah. sauce 一样啊，我不懂，你可以 try 一下写下来。Try right now. Argue that they are the same. Okay, so just now we say that we can have a different basis that give you the same topology, right? So maybe we can ask, is this set C here the smallest set where you can find? Where the smallest set they can find for your tau. Okay. If it is not, you can give an counter example. Okay, some set that satisfy this C condition here. I can build tau, but I can use smaller, okay, less item, okay, to build tau. Or another obvious question that we discussed before is whether this C is unique or not. Or even I give you way to produce already, or maybe it's not unique. 什么叫 mass produce? 量产 How to say? Duplicate. 好，讲理解在这里，没有 get 到啊？I wouldn't say 重复 but maybe you will build unnecessary basis element， 多余的，不需要，但是我还是可以放进去。Does it make sense? Even I give you a way to produce already, you still can produce different things. Yeah. Okay. Yeah, but still give you the same topology. The point here. Okay, the point here is we're talking about the same topology. Okay. OK， 就算我跟你讲方式怎么做你还是可以做不一样的东西出来。Yeah. Yes. Can you think like that? 这 C 把什么很多 open set 变成很小的一个 open set。上面的 lemma 这个 lemma 反着过来。let me think 啊，可以这样讲吗？kind of, yeah, opposite, yeah, because this one is you start with a topology, and then okay, you start with a basis, and then you look at the topology. Now you use the topology and then find the basis. And then the open set you take here is sounds very special open set. So later we'll see an idea called covering, cover. So you can see that this C kind of cover point in all the X. 可以想到 cover 吗？现在，因为你想一下 every point that live inside an open set，OK？、你拿一个最大的 open set X，the largest one，每一个点哦 ，every point in X 哦 ，there will be some C that cover this X here，contain this X，保护着这些 X。It's like covering here. Okay. Okay 吗 ？Okay. Yeah. Later we'll see idea of covering. But it's not very important here yet. Next. Next lemma, I think I don't want to prove, but I want to tell you. Next lemma, let B and B prime be basis for the topology T and T tau, okay, respectively on X. And then the following two are equivalents. Okay, this is a very good exercise you should try at home. Very mechanical one. First is, if we say that T prime is finer than T, okay, second hour, test you. T finer than T prime means what? Which one is a subset of which? T is a subset of T prime, okay? Then, if and only if, for every X in X, and for every B in B, okay, this coming from where? B coming from tau, such that for every X in B, there exists a B prime in B prime, such that B prime here will contain X and contain in B. Okay, makes sense 吗？你看 here demonstrate what final means 哦。每个 bit B here, you will find a smaller B prime. Final. Okay, everything in tau, every B in tau, you can find a B prime here. So here we are not talking about open set. We're talking about basis element, 更小. Okay, the basis elements. Then every B in tau, we can find a smaller B. Okay, 不要 confuse 啊，你不要又 confuse 啊，你看 B prime 在 B 这边又反了，不要 confuse 啊，不要 confuse， 要记住那个 idea， 不要 confuse。OK， 你看会 confuse 嘛 ？B prime 应该活在这边嘛，它又反了。Yeah. Sorry. Yeah. So don't be confused 啊 ，try and show this。等你 show 出来，你就觉得哇，很神奇，怎么会反的？怎么 basis element 的也是反的 ？Yeah， 还有个 subset， both of these are set。这个是这个 what is this 啊 ？B prime is a set of basis element. These are the basis element. So they are element. Okay, try and show this. This is kind of fun. Okay, so this will justify the final means of why is it final here? Why T prime is final? Then because you can see smaller. Okay, try and show this. Let's see. All right. So let's give some examples here. This one, I think, fun exercise to try. I will put out the solution also. This is very fun exercise. Please try. Fun exercise. Fun exercise. Okay. 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 So let's look at some examples here. Consider the Euclidean topology of R2. Okay. So there are two topology here. So one, we call it a TB. One is a TB prime. Okay. So generated by B and B prime, respectively. Okay, so what are these B and B prime here? So it's exactly what we draw just now. One of them we take open ball. So all the open ball. And then the other one we take open rectangle. Okay. So one thing you want to prove that is they form a basis, okay? And then you can show that. Wait, exercise is prove that TB and TB prime are the same, actually. And then before that, you can prove that B and B prime are basis for topology. Okay, use the same notation. Use the same proof that we had just now. Topology. Okay, so well, if you go back and go through this proof, I can summarize this proof for you. What you need to do. Okay, the three proof you need to do is summarize in three picture here. Okay, let's do X. X, the same X, huh? So for every point, if you want to show its basis, two things, right? For every point, you need to be able to find a basis element that cover your point, okay? Contain your point or cover your point. Second, the intersection property. So if you look at any two intersection of your basis element, what do you need to do? Okay, so you look at every point inside your intersection, you should be able to find another basis element inside this intersection. Okay, and then the third one, how to show that they are the same? One open, a set is open in one topology, is open in the other topology. Okay, so for example, why circle is open in the other topology? Because you can find a rectangle inside your circle. The other one, why the circle, why the rectangle is open in the open ball topology? Because you can find a circle inside your rectangle. Okay. Wait, how to find it? Then you need to write down. You need to go and measure. Okay. Yeah. I think I put this as the calculus 2 assignment, right? If you remember, go and dig your calculus 2 assignment out. Okay. Okay, from what you can see here, actually, these two things will give a basis for your Euclidean topology. Okay, actually, if you want to check, this will satisfy this C condition here, the script C condition here. Okay, the script C condition, you can check. Okay, it satisfies the script C condition here. But since you have two sets that satisfy the same condition, right? How about union of them? Still satisfy the same condition. Okay, so this solves the question I gave you just now. It's not unique. Because if you have two different sets, you combine them together, still set that satisfy the script. Okay. I mean, if you produce two, it's already not unique. But after you union them, then you can see that Actually, they are larger set, larger, but not sure how you count it because if they are uncountable, I don't know how you differentiate them. But this is the idea. Okay. Okay, let's look at more examples. Okay, let's look at more examples on a real number. So we want to leave our boring Euclidean topology. Okay, let's consider R with different topology here. So let's consider R with 3 different topology. So how we define this topology here? I'm not going to tell you who are open, but I just specify who are the basis element. Okay, then you should know that the open set that is just union of these basis element. Okay or not? It's very convenient. So let's recall the standard one, the Euclidean topology. Who do you think is the basis element here? What's the basis element in your standard topology? These are the open intervals. Okay, these are the open intervals. Open ball, we keep talking every time. Okay. So we can take a open interval here. A, B. Okay. A, B here. What else we can do? 你们有没有想过怎么我们不要用 half open 的 interval 来教 open 现在我们就做了。Okay, we will call the half open interval to be basis element. Okay. 现在我们把这些叫成 open set MA2 有教这个吗 ？MA2 有教这个吗 ？MA2 有没有？MA2 有教这个吗 ？Half open interval 是 open set， 有教还是没有教？有教吗 ？Half open set 是 open set， 有教吗？is never over close 你看 MA2 就少了一点乐趣了。我们现在有新的 topology 在这边 ，This is called the lower limit topology. The hell? Okay, maybe later will be apparent why we call it a lower limit topology. Okay. But you can see at the lower point, we take it. We take it. Right or not? We take the left endpoint. We take it. Okay, later will be more apparent why we call this a lower limit topology. 还有一个 topology 更神奇的。So, okay, let's tell you the cool name first. This is called the K topology. Okay, or we call it a RK here. So this K is just a set. So what set is this? This is the set of 1 over n. When you see 1 over n in analysis, right, you should be quite sensitive here. Something on Archimedean property should happen here. Okay, 1 over n. Okay, so what are the basis elements here? So we would declare that the usual one, the open interval, still the basis element. Standard topology is inside here, but we take an extra stuff. These are the complement of K. Okay, so meaning you can take A, B, and then take away K points here. Okay, so what are the picture here? So you got a AB open interval here. And then if your AB turns out to be near the 0 point, so let's draw this a little bit bigger. -1, 0, and 1 here. And then let's say we take an open interval around here. Then you will take away some point here. What are the points you take away? 1 over 1, 1 over half, 1 over third, like that. Okay, you will take away this denumerable point here. So one exercise you do is try and prove that these are the they form a basis. Yes? Yeah? 拿到玩什么 1 over 1干嘛？会被拿掉，但是我的这个呀会被拿掉。你的 point between 1 over 1 over 3还在啊 ，right？ 还在啊 ，carry on 了。The point between 1 over n and 1 over n plus 1。我觉得你们对这种 set 有印象嘛，对不对？你们不是有，我记得你们 MA 有一个 assignment 吗？不是 look at the 1 over n set of 1 over n。爸有印象吗？怎么我比你还有对你的功课还有印象？Yeah. Sorry. Be careful 啊 ，Be careful 啊。OK， 你讲一个点不会活在任何的 open set 里面。Is it true？ 可是我们也有拿 A 到 B 里面也是，我们全部都有。其实，说这个很特别，是不是？怎么有 Euclidean topology 加了过后变不一样东西出来？呀，这个蛮特别的。OK， 它不是回去 Euclidean topology 哦，它造出不太一样的东西。Later we will I think we will. Yeah, we will. I mean now we will do now actually. So actually should I show you what time is it? 11:38. Okay, I don't want to show you how to prove it, but I want to tell you what's the relation between them. So lemma here. So let's see what's the relation between them. The topology, so okay. So we say that RL and RK actually are strictly finer than the standard topology. Okay, strictly finer, meaning what? They contain Euclidean topology actually. Okay, 所以你会觉得说，哦，我把这个 A 收起来过后，可能比它小，actually it's not. Actually it's not. Okay, they contain Euclidean topology, but we can't really compare RL and RK. 我们不能讲谁在谁里面。Okay, it's not comparable between RL and RK. Okay. Okay, so the reason why we want to abolish MA2 is because MA2 is just this one. Standard topology of time. Okay. So if you learn general topology, you will learn more general topology that we can put. Okay. Okay, so the proof I can show it to you. It's very simple one. Okay. Let me show you what's the proof. What's the technique used in proof? I won't tell you how to prove, but what's the technique used in proof here is just let me show you using this now better. Okay, it's just a sum set theory. Okay, how you write one open set in the other open set using union. Using union is enough. Okay, that's all. Okay, based on set theory. Okay, it's a very good exercise that you should try. Okay. Okay, let's continue first. I think let's take one more basis. I think we are very good already. Okay. Okay, next basis we want to define is called subbasis. Like vector space, subspace, so subbasis. So we put a script S here. X is a collection of subset of X. Again, you see, whenever we define basis, open set, these are all just subset of X. Okay, we just start with subset of X that satisfies some property. Okay, some property here. So here is, we just take anything that's a union that equal to X. Meaning what? Actually, basis element also satisfy subbasis condition. Okay, but the difference is here. The difference is here. Topology generated by subbasis is different on how we define topology generated by basis. Okay, here is the difference. The generation is different. Okay, 就是说可能原材料都一样做米露的原材料都一样，但是澳洲的就是比马来西亚好喝。有些人讲不是我讲有些人讲好喝。为什么比较好喝呢？因为它造的成分不一样。OK， 为什么？为什么有些人喜欢喝澳洲的米露？因为它比较多的大麦的味道 ，malt。但是呢，马来西亚的是为什么呢 ？cocoa 比较多巧克力味。OK， 说成分不一样，材料用的都是一样，而且现在做的那个方法不一样。So how do we generate using subbasis here? So this is defined to be the collection. Again, collection 还是 collection? Collection of what 呢？Collection of all union. Union of what 呢？Union of finite intersection. 有点绕Okay, union can be arbitrary, but intersection has to be finite. 但是这个没有 violate 那个 open set 嘛 ，open set 一定是 close under finite intersection and then close under arbitrary union. Okay. So how can you imagine the elements here 你应该怎样把它写出来这个 TX 里面长怎样 ？Is a union of some B alpha such that 这些 B alpha could be some finite intersection. Okay, of Xi. So 这些 Xi is coming from the subbasis 那个 collection of set that union to be X So 我们也可以把这句话翻成symbols So our set X is all the Xi as a subset of X such that the union of Xi is X. Okay, so 你看如果你记不起字这两行你一定要记起来，这两行把前面的字 describe 完了。Okay, subbasis is a collection of subset that union you get the whole space. Okay, and then your topology is generated by subbasis means what? Union of finite intersection. Okay, union of finite intersection. Okay, Lydia, 到这里你应该问个问题是不是 ？Why is this a topology？ 对不对 ？Why is this a topology？ 长得不是很像对不对 ？topology 要符合那三个条件Good. So sanity check. Check that this is a topology. Okay, check TX is a topology. Okay, so please check it. There are some examples here. I gave you some examples. Please check it 像我们刚才做的。So one example is for example the Euclidean topology. Okay, the Euclidean topology can be generated using subbasis. 你可以想想看嘛 How do we produce this AB here? Open interval AB using finite intersection of something. 你可以想想看 But one way to do this, you can consider the intersection of two infinite open set. Okay, one way we're gonna do this is using infinite open interval. Which infinite open interval intersect can get open interval AB? What do you think? You could go from A to infinity and negative infinity to B such that the open interval AB is just the intersection between A to infinity up to negative infinity to B. Okay, when we write these, you should draw some picture inside your mind. Whenever you have open interval, please draw this real line inside your mind here. Okay, so what we're gonna do is we're going to take the infinite open interval from A to infinity and the open interval from B to negative infinity. Okay, so there's such that their intersection lie in open interval AB. Okay, please draw inside your mind. So meaning what? Meaning we could take, so hence the collection of infinite of all infinite open interval form a subbasis. Okay, form a subbasis for since the open interval form a basis. This is one subbasis you can take. I didn't say this is the only one. Okay, this is one of them. Okay, so there are multiple ways you can see our Euclidean topology here. Second, what else? How about we look at the topology generated by open rectangle? Can you think of a subbasis for it? Can you use intersection to build your open rectangle or not? You can play the same game, correct or not? Half infinite rectangle. Is it what we call it? Half cylinder, maybe? Half cylinder. Half strip. Half strip. Half rectangular strip. 也可以嘛，对不对? But instead, we can take consider subbasis containing vertical and horizontal infinite open strip. Open strip. Okay, so I claim that you can use the intersection of these two to build open rectangle. Is it true? Okay, let's draw it. So let's say you have a horizontal strip like this, right? Okay. And then you have a vertical infinite strip. This. Okay, then their intersection is a open rectangle here. Okay, now. Okay. Okay, so before we leave, I give you one last proposition here. Or proposition. If you take S to be a basis for the topology T, then the claim is the topology in general, the topology generated by this subbasis is actually finer. Okay, it's actually finer than the topology T generated by the basis X. Okay, just now I gave you examples that they are the same. Okay, but in general, TX should be finer. So the proof is just TX will, which one is finer? Yeah, TX. So TX will contain T. Okay. Because in subbasis, you consider more things, intersection. But X layer, you just union them. Does that make sense? You start with the same thing. Just now I already tell you, right? Basis also subbasis, right? Because you union all the elements, you also get X. But the way they generate is different. Okay, so the difference here is the way they generate is different. One is generate using subbasis method. One is generate using basis. Their ingredient is the same. Okay. Okay, because subbasis you consider intersection also, finite intersection. But basis left, you just union. Just now we proved already, right? The topology is just the union of these basis set. Okay. Any question before we finish? No. And next class, we'll go into subspace topology, and then we'll talk about Hausdorff space. Okay, see you tomorrow.